given a measurable space E with sigma algebra E, we consider the real measures on it. Right? So the measures with values into R. And so what we did for any mu real measure, we saw that the absolute the total variation measure is a measure, so it's positive value is a measure. Now, what we are going to do is so for any such measures, we define the total variation, also called total variation mass, total variation, the total variation of the whole space E. Okay, so now we are going to prove a theorem that says that, so first of all, this total variation norm of total variation mass is a norm on the vector space MEE, the space of real measures. And second, we're going to prove that this vector space equipped with this norm is complete, and therefore this is a Banach space. Okay, so let's prove this theorem. So let's first prove that it's a norm. So proof. So for any mu and nu real measures, we want to check as a first thing that if we consider the sum of the two measures and we take the total variation, then this is bounded by the total variation of mu plus the total variation of nu. Okay, so by the definition of the total variation, so we decompose the space as a countable disjoint union of elements in the sigma algebra. And then what we do, we say, okay, then we know already that if you take the measure of each set an, this is, okay, by definition, this is the measure of the set an plus the measure of the set, the new measure of the set an. And of course, this is, so this is a norm. So this absolute value is just a norm on the real numbers. So this is less than the absolute value of mu of an plus the absolute value of nu of an. Okay, so now we sum over n, and what we get, so okay, we sum this sum over n plus this sum over n. So here we get sum. That's better to start a new page. So we have a sum over n of mu plus nu of an is less or equal than the sum over n of mu of an plus sum over n of nu of an. Okay, so now this number here is a bound from below of the total variation of E. So this is mu, or total variation mu of E. And the second one is the total, is bounded by the total variation of nu. Okay, but now what we have that this set an was arbitrary, and taking the sup out of all the decomposition of the space of this quantity, we get, by definition, the total variation. So since an was arbitrary, what we get that the total variation of mu plus nu is bounded by total variation of E plus total variation of E. Okay. So therefore the total variation satisfies the triangle inequality. Okay. So total variation satisfies the triangle inequality. Now let's check that the only measure with norm 0 is the 0 measure. So now, okay, also let's observe that that is homogeneous. Observe that the total variation of lambda mu, this is just the absolute value of lambda times the total variation of mu. Okay. Now I said regarding the 0, so if you have a total variation 0, then what is okay? And this means that the total variation of the whole space is 0. Then what does it mean? Then so we know that whenever we decompose the set E, the sum of the absolute values of mu of the decomposition gives 0. So in particular, then if I take any set in E, then what I can do, I know that first of all that the measure of E in absolute value is positive. To this number I can add the measure of E of A plus this other positive number, the measure of the absolute value of E minus A. Now A, and the complement of A, this is a decomposition of E, and therefore this is bounded by is bounded from above by the measure, the absolute value, the total variation of E, and this is 0. So since this is 0, then what we have that mu of A is 0 for any A, so which means that mu is the 0 measure. Okay, so we conclude that the total variation is a norm. Next, we check that this norm is complete. So let's check that the norm is complete. So what we do, we take a sequence of measures that form a Cauchy sequence with respect to, so sequence in mu E with respect to the total variation. And then what do we do? Okay, first of all, let's fix whenever any set in the sigma algebra, then for any n and m natural numbers, we have that if we consider the measure mu n of A minus mu m of A, this is bounded by, so this can be seen as the measure mu n minus mu m applied to A. And we know that the measure is always bounded above by the total variation measure A. And we know that the total variation is a measure, so it's particularly monotone. So this is bounded from above by mu n minus mu m of the whole space E, which by definition is the total variation of this difference. Now, what we know that the sequence is Cauchy, so this number goes to 0 as mn goes to 0, right? So what we proved that this sequence of numbers, they form a Cauchy sequence of real numbers. So the sequence mu n a, now see that these are real numbers, and they form a Cauchy sequence in R, and R is complete. So the sequence converges to a number, real number, which we denote by nu of A. Okay. Now, for any A, we associate a number called nu of A. Okay, what we need to show is that this nu form a measure or real valued measure, and mu n, actually they really converge in norm to mu. Okay, so take a sequence AK, disjoint, or a decomposition of sets, or like disjoint sets in E. I need to show this a real measure, right? Okay, so what we know is that for any k, mu n k, as n goes to infinity, converge to nu of an. Okay. Now, I want to see this as a convergence of functions. So let me open a parenthesis here. A parenthesis. Okay. So suppose that you have numbers depending on two indices, two natural indices, a and k, of non-negative integers. Then I claim, so we claim that if you sum over k the limit in M of a and k, this is less or equal of the limit of the sum, or the limit in M going to infinity, the sum over k of a and k. Why so? So I want to prove this using Fatu's lemma. Okay, so we may apply Fatu's lemma to the functions. So the functions, let's call it f of m, they are defined on natural numbers into R, set as fm at the number m is equal to a, not m, at the number k. This is a m k. Okay, so these functions we can integrate with the counting measure on n, and what we have that the integral of fk is equal to the sum over k of the values a and k, right? So in this space n with the counting measure, we can apply Fatou's lemma to functions. And what does Fatou's lemma says? Tells us that the integral of the limit function is less or equal than the limit of the integral of the functions. But now in this case, the integrals, they're just real sums over k. So this is true because of Fatou's lemma. Okay, so now we are going to apply Fatou to a sequence of numbers. Okay, now, so hence what do we have? We have that if you sum over k, mu n ak minus mu minus nu ak, okay, we can bound this as okay, nu, what is nu? Nu is so you have mu of n ak minus limit over m of mu m ak. Now these are just numbers, this absolute value, everything is continuous, so we can write it as sum over k of limit for m going to infinity of mu n ak minus mu m of ak. Okay, so now see, let's call these numbers, these are a, m, k, or no, but better, these are the numbers a, m, k, and n is fixed. And so now we apply the Fatou's lemma, and I can swap the limit with the sum, with the bound. So you have Fatou, then you have, okay, in general you have the limit as m goes to infinity of sum over k of mu n ak minus mu m of ak. And now ak is a decomposition, they are disjoint sets, so we can even complete them with a disjoint decomposition of E. And what we do, we can bound this sum with the total variation of the difference mu n minus mu m. And we know that this number, since mu is Cauchy, this goes to 0. So we proved that this sum as a function of n goes to 0. Okay. So we're ready to finish the proof that nu is a real measure. What we have to prove is countably additivity. So if you have a disjoint family, the mu of this union is the sum minus the sum of ak. So what we want to show is that this is equal to 0. But what we could do, we can bound this as okay, nu k ak. Let's do the triangle inequality with mu n uk ak plus, now I would write the same thing, but now actually this number here, since ak since mu n is additive, is sigma additive, this is the same of writing the sum over k of mu n ak minus the other sum of mu ak. Right, so these two quantities are the same. Right. Okay, so now this is a set, And we know that this sequence of measures on this set, they converge to this. So this number goes to 0. And we just proved that in the previous page here, we proved that this sum goes to 0. Okay, so what we have that we proved that this goes to 0 and this other element goes to 0 when n goes to infinity. But this number is independent on n, so it means that this number is 0. So we have that the measure nu is indeed a measure. Okay, so now let's prove that the convergence of mu n towards nu is in respect to the norm. So also, so if you have to do mu n minus nu total variation, okay, by definition this is mu n nu applied to E, and this by definition is the supremum of all the sums over k of mu n minus minus nu applied to ak, such that E is decomposed disjointly by as a union of ak. Now, the calculation above tells us that this number is less than the absolute, the total variation. This calculation here. This number here is less than the total variation, right? So what we have now, this calculation above, which is just by phi 2, tells us that this quantity is less than the lim of n of f mu n minus mu m total variation, and this number goes to 0. Good. So we finished the proof of the fact that the real measures on a fixed measure space equipped with the total variation norm is a Banach space. I will add now some extra information about how one can decompose a real measure in the difference of two positive measures. This decomposition has the name of Hahn decomposition. So for a real measure, let's call it mu on a measure space, measurable space E, we defined mu plus to be 1/2 of the total variation measure plus the measure, and mu minus to be 1/2 of the total variation measure minus mu. Okay, so that we have that mu is for sure just the sum of mu plus minus mu minus, but now both mu plus and mu minus are positive measures. And this is just because, remember, we proved that the measure of a set is bounded, the absolute value of the measure of the set is bounded by the absolute the total variation measure applied to A, right? So which means that when you apply, this number is always bigger than this, and this number is always bigger than this, applied to any set A. Okay, so these functions are valued into the non-negative numbers. Okay, so now what is interesting about now having a decomposition like this is that we can define the integration with respect to mu as just the difference of the integration with respect to positive measures. So we define the integral with respect to a real measure So suppose you have a map from E to R, and let's assume that it is integrable with respect to the absolute, the total variation measure. So this integral is finite. Then we define the integral with respect to the mu as the integral of f in the mu plus minus the integral of f in the mu minus. So this property here ensures that each of these numbers are finite. So the difference is, well, can be considered. So it's not an indefinite form. So this definition is well defined. And you have the other properties like it's linear. So it's a well it's a good definition for integral. Okay, I'll tell one more property about this decomposition, but I will not prove it, at least for now. So we wrote mu as mu plus minus mu minus, but there's this fact that there exists a set B in E, which is unique up to null set, so sets of mu measured 0, such that mu plus is equal to the absolute value measure restricted to B, and mu minus is equal to the total variation measured mu restricted to B complement. Okay? So in other words, what I'm saying is that for any A in E, mu of A is the is mu is total variation restricted to B minus the total variation restricted to the complement of B. So in other words, the way you can think of is, given a measure mu, then real valued, then you are decomposing the whole space E into two sets, B and the complement, in such a way that on the first set the measure is positive, and the second where the measure is negative. So really, I mean, this decomposition really is saying that every real valued measure is the sum of two real measures that have disjoint supports. So if it's the set where this is non-zero, the smaller set where this is non-zero is a zero set for the other. Okay.